Okay, today we will continue with Thevenin and Norton and look at a small example. And in the next class, two big examples. So, brief recap. These are known as equivalent circuits based on theorems that were proposed more than 100 years ago. And the first one was proposed by a French telegraph engineer named Leon Charles Thevenin. So, the theorem is named after him, Thevenin theorem. And a few decades after that, an American engineer proposed his own theory based off of Thevenin's theorem that come to be known as Norton's theorem. Both of those state that you could take a large circuit comprised of voltage and current sources and linear components like resistors, and you could represent the entire circuit as a single voltage source in series with a resistor, or as a single current source in parallel with a resistor. And I brought up this example. This is a random circuit which has a component R6. And I was making an example of if you were a design engineer trying to find a particular value for R6, you would analyze the rest of the circuit without R6 and represent that entire circuit as a Thevenin or a Norton equivalent circuit, right? And so we can perform analysis on the circuit using the techniques that we already studied. This is not a new analysis technique. Okay, Thevenin and Norton equivalent circuits is a concept, is a new concept based on two theorems, but it is not a new analysis technique. You will simply apply the techniques that you have already learned so far to determine the three quantities that are presented here. Okay, we have Thevenin voltage, Thevenin resistance, and the Norton current. Okay, so those three are the quantities that we will determine using our existing techniques. Oh, one other thing is that the Thevenin circuit shown here is equivalent to this large circuit. And the Norton circuit shown here is also equivalent to that large circuit. So if A equals X and B equals X, we can state A equals B, meaning the two circuits are equivalent to each other. The Thevenin circuit for a circuit is equivalent to its Norton equivalent. And we can extend that and imply a new technique known as source transformation, which we'll put a pin on it and look at it at the end of this chapter. Okay, source transformation is a technique that can be utilized to change or transform a voltage source into a current source and vice versa. Again, it comes from the fact that a large circuit can be represented as a Thevenin or as a Norton equivalent circuit. Okay, one final thing is this. We have voltage, resistance, and current. Ohm's law can be used to relate the three quantities. So VTH, Thevenin voltage, is equivalent to Norton current times the Thevenin resistance. So obviously, if you have two of these values, you can find the third. So some books and some instructors like to say that you could first find the Thevenin resistance, then find the Thevenin voltage, and then use those two to calculate the Norton current, which I absolutely do not like. Okay, that is the wrong way to actually teach students. RTH, Thevenin resistance, is by far the easiest. Okay, you're simply finding Req for the circuit, which is something you have done in your physics class. It is something also you have done at the beginning of this chapter. Finding the total equivalent resistance for a network of resistors, right? You have already done this before. So finding Thevenin resistance is by far the easiest. And Thevenin voltage, kind of the same as Norton current, but typically you have to modify the circuit for Norton current by placing a wire at the end. So some books and some instructors like to say, let's not deal with that. Just find the Thevenin voltage and then apply Ohm's law. The problem with that is, if you have the two quantities and you try to calculate the third, you have to be absolutely certain that the two quantities you have, the values are absolutely correct. Because if even one of those quantities is incorrect, you now end up with a second incorrect quantity. Make sense? All right. That's just one of the reasons. The other reason is sometimes it is not possible to calculate RTH. You cannot calculate REQ because some circuits are not reducible. Simple circuits, yes. Large circuits, not. Okay. So in some cases, it is not possible to reduce the circuit to REQ. Also, if you have dependent sources, which you have not studied yet so far in this class, if you have dependent sources in there, you cannot eliminate those dependent sources to determine REQ. So for those cases, you cannot find RTH. You have to find IN and VTH and then calculate RTH from there. Okay. So we have three quantities. We will find all three of those independently: Thevenin voltage, Norton current, and Thevenin resistance. These two summary slides are the most important. Okay, these two summary slides are the most important. Again, this is not a new analysis technique that you're learning. You're simply applying it to a concept. So to understand the concept and setting up the problem, that is the most important. Okay, you have three quantities. You have to perform three separate and independent analyses to determine each one of those three quantities. First things first, if the question states, find or determine the Thevenin and Norton circuit as seen by a particular component. That component should not be part of your analysis. That is the absolute first step right at the top. Okay. If it states analyze between terminals A and B or terminals X and Y, then go right ahead. You can begin your analysis. You do not need to remove anything. But if it says the phrase as seen by a particular component, then you remove that component from your analysis. Similar to how we saw in the opening example where I had R6 and I said you analyze by removing R6 at the top. That is what you do here. This phrase is also written as a load circuit or a load network. Electronic circuits are usually multi-stage operations. As an example, simple audio equipment, you would have a preamplifier followed by an amplifier followed by a speaker. The speaker is actually the load for the amplifier, but the load for the preamplifier is the second stage, which is the amplifier. So preamplifier, amplifier, and speaker. Each succeeding circuit or each succeeding stage is the load for the previous stage. So the speaker is the load for the amplifier is the load for the preamplifier. Make sense? If you look at any speaker specification, it will always state the impedance in ohms, either 6 or 4 or 8. So the output for any audio video receiver that you connect to your speaker systems or your speaker will always have an output rating stated in ohms. If you have easy access to the back of your audio video receivers, you can take a look, or you can download any manual for any brand and it will state in the specifications what the output impedance is. The reason is we want it to match next succeeding stage. And that would be the Thevenin resistance of the preceding circuit. So if it says as seen by or load circuit, you remove it from your analysis, you modify the circuit 3 times, and you perform 3 separate independent analyses to determine each one of those 3 quantities. The results you obtain from any quantity or from any analysis does not apply to the other 2. meaning if you analyze for Thevenin resistance, the values you obtain there do not affect the other two. If you obtain Thevenin voltage or Norton current, it does not affect the other two quantities. Okay, all three of them are three separate circuits. When it comes time to perform your analysis, you can choose any technique you wish. You've studied mesh current analysis, node voltage, superposition, Ohm's law, KCL, KVL. Does not matter what you choose. Any single technique or a combination of those techniques, and you determine your quantities. But absolutely do not use Ohm's law at the highest level. Highest level meaning you do not use it to find Norton current directly. Okay, you can use Ohm's law as part of your analysis, but not to find Norton current directly. Does that make sense to everyone? Right? Any questions? Yes. Because I don't want you to. I want students to learn how to find or determine each quantity independently. Yes. That is absolutely correct. So the question being asked is, well, the first question being asked was, why can't we use Ohm's law? Well, the answer is because I want students to learn how to determine each quantity independently. And then the second question being asked was, can we use it to check our work? That is actually part of, that would be, the answer is yes. And that is something that I also put in the final exam. Use Ohm's law to verify your answers. So again, I'm repeating this. If you have not yet taken a look at the final exam, the page has been up since the first day of the class. The final exam page will list Thevenin and Norton as a 30-point problem. It assesses everything from chapters 1 and 2. It's a big 4-page problem. It'll test node voltage, mesh current, voltage division, current division, REQ, everything. Okay, it's simply 4 different problems rolled into one. But again, it has it has subsections to it. So when I say it's one problem, doesn't mean like it's, you get it right, you get 30 points, you get it wrong, you get 0 points. That's not the case. It's broken up into multiple pieces. All right, any other questions? Okay, so 3 quantities, what do we do? We have open circuit voltage, short circuit current, and equivalent resistance that we will determine the 3 quantities. So I'm going to draw a random circuit. You don't have to draw this out. But let's say you have a voltage source, resistor, and then multiple components down the line, and the current source, resistor, resistor, resistor. Now, first, you have to establish your terminals of analysis. If it states terminals A and B, terminals X and Y, then you jump in right away. If there's a component connected to it, then you remove it. You have your terminals A and B. At this point, you don't do anything to the circuit. You simply apply your analysis technique and you find the open circuit voltage with the polarity shown. The resulting voltage could be positive, could be negative. Doesn't really mean that your answer is incorrect, right? But you analyze with the polarity that is shown here between terminals A and B. Your open circuit voltage, actually, your Thevenin voltage is the open circuit voltage, VOC. Again, you do not make any modification to the circuit except to establish the analysis terminals. That's it. So establish the analysis terminals and simply determine the voltage at those open terminals. And that would be your Thevenin voltage. Yes. So the question being asked is if the polarity would always be given. Not necessarily. Sometimes it may be given, sometimes it may not. You would simply assume a polarity and do your work. Students can choose to use the opposite polarity, which is absolutely fine. You could have minus at the top and plus at the bottom. It doesn't really matter. Because once you finish your analysis, your answer would match the polarity that you assume at the beginning. This is just the standard. This is just the standard that's been there, for decades. If your logic tells you that it should be opposite, then choose the opposite. Doesn't really matter. Yes. Yes. So the question being asked is, are the terminals where we remove the component? And the answer is yes. If the question states, find it as seen by the component, then we remove the component. If it says, analyze between the terminals, then we simply analyze between the terminals. Then we do not need to remove anything. Okay. Let me be clear about that. You remove the component only if the problem statement states it. If the problem statement asks, analyze between terminals X and Y, then you do not remove anything. You simply begin your analysis. That makes sense to everyone? Right? So again, Thevenin voltage does not require any modification to the circuit, except at the beginning if you need to remove the component. Norton current, however, you need to analyze for current. Current needs a pathway to flow through. If the terminals are open, there is no current flowing through those terminals. So we place a wire between those terminals, A and B. Again, if there was a component and we had to remove it, then we removed it. But now we place a wire between it. And because the polarity we chose was plus at the top, current goes from plus to minus. So the current is flowing in the downwards direction. We label that current as ISC, the short circuit current. And the Norton current is that short circuit current. Again, you can use any technique you want to determine Norton current or Thevenin voltage. Node voltage analysis, mesh current superposition, Ohm's law, KVL, KCL, any technique you want. So choose any technique you want and you analyze and find the current between A and B. Because we place a wire between those terminals, the circuit changes. Okay, if there's anything connected in parallel to that wire, it'll be shorted out. Okay, even if there's no component connected, if you see, let's say, so here, I'm just going to call this Rx. This Rx resistor is in parallel with the short circuit wire. So that changes the circuit completely. With or without Rx in there, the circuit still has changed, right? In VOC, Thevenin voltage, Rx would have been part of your analysis. For Norton current, Rx is not because it shorted out the wire. Okay. So again, take your time, set up the problem correctly, following the steps, and then begin your analysis. Do not jump in without drawing up the circuit diagram, without actually creating the setup of the problem. Otherwise, you'll end up incorrect. All right. So that is the only modification you would make to analyze for the Norton current. Does that make sense to everyone? Any questions so far? Again, you're not learning a new technique. You're simply applying those techniques to a new concept. All right, RTH. RTH is simply REQ as measured between those open terminals. But you cannot measure REQ if you have voltage and current sources present in the circuit. You always have to disconnect all the energy sources in the circuit before you measure your resistance. So the way we remove the voltage sources is by applying the concept we learned during superposition. We reduce all sources to zero. Voltage sources are replaced with a short circuit. Current sources are replaced with an open circuit. The only thing left in that circuit now are a bunch of resistors. You find Req between those open terminals, the total equivalent resistance, and that is your Thevenin resistance. That's it. Anything new in there? No. It's just the application, right? The concept of reducing the sources to zero, which you already learned in superposition. And then Req is something you've learned in physics. You've also learned at the beginning of this chapter. And that's it. So in the few minutes we have left, let's look at a straightforward example. Here, the question simply asks, find the total equivalent resistance, the Thevenin resistance between terminals A and B. It does not say as seen by, or if the component is a load or a second network or anything like that. So there's nothing to modify, there's nothing to remove. We simply begin our analysis. We need to find Req between A and B. So what do we have? We have 4 resistors in the circuit, 3 voltage sources, and 2 current sources. What happens to the voltage sources? Circuit right there. R1, R3, R2. V2 is again a short circuit. Now I am marking out the place where the sources were connected. You don't have to do so. I'm just using it for explanation purposes. You don't even have to draw the wire for a current source, right? Current source is now gone. So this wire basically has no purpose. And there's another short here, another short here. And then we find Req between A and B. To find Req, we always go to the farthest end. When I go to the farthest end, I see that R1 is now connected to R2 due to the short of voltage source V1. So they are in parallel, which that combination is then in series with R3, and that entire combination is in parallel with R4. And that is my Req. If you are comfortable with a particular technique to determine Req, you can stick with that. You can use the 2 techniques I showed in class. Your choice, your wish. This is the only circuit that requires removal of the sources, okay? Do not remove sources for the Norton or the Thevenin circuit. Because if you remove any of the sources, then circuit's completely changed. It's incorrect. So make sure you understand the concept of setting up the problem. Homework for Thevenin Norton, I believe, is due Thursday. We will look at a couple more examples on Wednesday, but get started on the homework. As I said, the concept is new, which has already been covered now. The analysis technique is not new. So get started on the homework. Reach out to me. Let me know if you have questions. But we'll end class here today.